Today we're discussing section 3.2 on quadratic equations, functions, zeros, and models. Here's our objectives for your notes. Really what we're looking at today are quadratic functions and equations. And we've thrown this term around before, but we want to start to really focus in on this particular function. There's a lot that you can do with it and a lot that you can tell about the real world using this function. So whenever we're talking about quadratics, we're going to assume that we can always write our function of the form ax squared plus bx plus c. Any function of that form with no other terms and where there definitely is an a term, our first term, that's called a quadratic function. A quadratic equation is any equation that can be written of the form with a quadratic function, but set equal to 0. And when we write an equation in this form, we call it the standard form. Whenever we talk about the zeros of a quadratic function, so something like ax squared plus bx plus c, the solutions of that associated quadratic equation are when you set the equation equal to 0 and solve for x. So if I ask you for the zeros of the quadratic function, you're going to set it equal to 0 and solve for x. Sometimes those zeros are also called roots. Now, there's some algebraic principles that we have to deal with when talking about zero products. A zero product is something where you have a number a and a number b, and they multiply to 0. When that happens, then one of those two numbers must have been 0. Alternatively, if you have a equal to 0 or b equal to 0, then of course their product must be 0. And that should feel familiar because, as you know, anything times 0 is 0. That's what that second line is really saying. That first line is why I always say if you have two things that multiply to 0, set both things equal to 0. And it comes from this concept. You'll see a bit of that today. Now, the other idea we have to think about is that if we have something where like x squared equals k, and we take the square root of both sides, that's typically how we would solve this, then you actually have to write that x could equal positive square root k, but x also could have been negative square root k. Because if I square this, if I look again at squaring both sides to see if I can get back to the original, then I'm looking at x squared equals negative root k squared. And when I square that, my negative becomes positive. What the? Sorry about that, guys. Hang on one second. Not sure how that happened. When I square that, my negative becomes positive, and my square root on the k cancels with the square. So I just get a positive k. We don't really need these parentheses. So now I have x squared equals k, which means the negative case here could have also been an option for x. And unless we write down that it could be the positive root k or the negative root k that squares to positive k, we could lose a solution in there. So you're going to see a lot more often now where we write x equals plus or minus the square root of k. And when you see that plus minus on top of each other, that means plus or minus. I apologize if you can hear my cat. She is making quite the comments right now. My goodness. So when we see this plus or minus, just think to yourself, okay, I'm going to write out that x can either equal positive root or x equals the negative root, okay? And that's exactly how I want you to write it. So let's see that in practice now. Let's solve something like 2x squared minus x equals 3. For this one, we have 2x squared minus x equals 3. We're going to subtract 3 from both sides. And we have 2x squared minus x minus 3 equals 0. And now here's where we get the fun of practicing how to factor. Oh my goodness, this is driving me nuts. We get to practice factoring with a 2 in front of our x. Like this. Usually the easy case is when we only have an x in our first two places, but here we have a 2, so we have to factor with a 2 and an x. Now I could either put the 3 here, or I could put the 3 here. If I put the 3 on the inside, like this, then I know I'll have a 3, and of course the 1 will go here, because these terms, the 3 and the 1, need to multiply to my 3 up here. So if I put the 3 here, I know I'm dealing with a 3 times x and a 2x times 1. So I'll have a 3x and a 2x. Oh, that tells me that'll multiply, or add to x here. If I didn't put the 3 there, if I put the 3 here and the 1 here, I could have a 2x times a 3 and a 1 times an x. But then I have a 6x and a 1x. I'm trying to combine to make a minus 1x, and that's just not going to work out. So I put the 3 here and the 1 here. If you're not sure and you don't want to think through all that in your head, just try it both ways, FOIL it out, and see which one works out or gets you close to the answer. But I do want to talk about signs next. So these signs on this are a minus 3, which means I need to have a plus and a minus in here. And I need to have a minus x in the middle. So my minus needs to go with the bigger of the two. So I need to have a minus 3 and a plus 1. Now that I have these two terms, I'm going to set each one equal to 0. So I do this the standard way, add 3 to both sides, and we get 2x equals 3. And then divide by 2 on both sides, and I get x equals 3 halves. I subtract 1 on both sides, and I get x equals negative 1. And there we have solved it. Amazing. Trickiest part here was definitely doing the factoring with the 2 out front. That'll take a little bit of practice, but it'll get easier to see. It's the same factoring technique as we had before, just getting used to more potential options. Now we're going to solve 2x squared minus 10 equals 0. Notice how this only has 2 terms, not 3. So I don't want your brain to go to factoring with 2 binomials, basically 2 terms with 2 terms each. I want your brain to go to, okay, what if I could just solve this directly? As in, what if I could take 2x squared minus 10 equals 0 and add 10 to both sides? Then I have 2x squared equals 10. So now I have x's on one side and non-x's on the other. That's a pretty good first step. So I divide by 2 on both sides, and I have x squared equals 5. Nice. Now I can just take the square root of both sides and look at x equals plus or minus root 5. Or we write this x equals root 5 or x equals negative root 5. So we didn't have to do all of the factoring techniques we learned before. There were only 2 terms here. There was no middle x term, essentially. And so we knew we could just solve it with some other standard algebraic practices. You can also check your work with these, which is nice. So I could actually look at what happens when I plug in x equals root 5. Then I get 2 root 5 squared minus 10. And hopefully this equals 0. Well, this equals 2 times root 5 squared. Well, those two cancel out, so it's just 2 times 5 minus 10, which of course is 10 minus 10, which does equal 0. Now we can check the negative case, negative root 5. So we're looking at 2 parentheses negative root 5 squared minus 10. And we're looking to see, does that equal 0 from the original question? Well, this gives us 2 parentheses. Now, I have a root 5 squared, and the root and the square cancel each other out. And I have a negative that's also in the parentheses of the square. So the negative's gone. So I'm left with 2 times 5 minus 10, which of course is 10 minus 10, which does in fact equal 0. So if we hadn't written the plus or minus in that square root, we would have missed this entire second solution to this problem. So it's super important moving forward that you get used to writing down plus or minus root 5, or plus or minus the square root of anything, for the rest of this course. You'll start to lose solutions and lose points if you don't. Now here's another example of what can happen. Notice how each of my terms here have an x value. And I have an x cubed to start. The only time you're going to get an x cubed is if each term has an x and you can factor it out. We won't be factoring cubics at this point in the course. So what I mean is we can take 3x cubed minus 11x squared minus 4x and pull an x to the front. So we have 3x squared minus 11x minus 4. Just like this. So I've taken an x out of each term, which reduced the exponent, or took the x away entirely in the last term. Now we have to work to factor this a little bit more. So I have x, we're going to ignore that one for a little bit, and we got to factor this 3x squared minus 11x minus 4. Well, the only things that can multiply to 3x squared are 3x and x. The only things that can multiply to a minus 4 are 1 and 4, or 2 and 2. This is getting multiplied with the 3 and the 1 that make up the first two terms here. So we got to think about, do I want to multiply my 3 and my 1 by a 1 and a 4 and hopefully add something together that makes 11? Or do I want to multiply my 3 and my 1 by a 2 and a 2 to maybe make up the 11? Well, if I look at 3 and 1 multiplied with 2 and 2, I'm looking at combining a 6 and a 2 somehow to make an 11. That's never going to make an 11. But if I multiply the 3 and the 4 and the 1 and the 1, then I have a 12 and a 1. Those I can combine to make an 11. So I want to use the 1 and the 4 for sure. And I want to put the 4 in a place where it's getting multiplied by the 3. So if I look at how foiling works, I'm either multiplying my outside terms or my inside terms. Well, if the 3 is going to go in this first place, then I want to put this 4 in this outside place so that my 3 and my 4 get multiplied together, which means my 1 goes in this place. Again, that'll let me have a 3 times 4, which will give me a 12x, and I'll end up with a 1 and an x, which is a 1x, and these two can be combined to make an 11x. That's kind of the idea here. So, going back to the original problem, we got to think about signs. So I have a minus sitting in front of the 4, which means I know I need a plus and a minus in here somewhere. They can't match in signs or we'd have a plus 4. So I need a minus in front of my bigger number, essentially. So the minus 11x is negative, and so I know I need to have a minus in front of my 4 to have the bigger overall minus 11 in the end, which means I get a plus here. So that's how this whole thing factors. It factors into 3 different terms. Now we have three things that multiply to 0, so we're going to set each thing equal to 0 and find our three different solutions. So we set x equal to 0, and that's going to be one of our options. We're going to set 3x plus 1 equal to 0 and solve for x. And then we're going to have x minus 4 equal to 0 and solve for x. So I subtract 1 from both sides here. I get 3x equals negative 1. So I get x equals negative 1/3. If I add 4 to both sides on the next one, I get x equals 4. And so these are my three solutions to this problem. I could plug all three of back into this original function, and I know I would get 0. It's a great way to check your work. Now we're going to talk about a new technique that's actually something you can use essentially to push a quadratic to be factorable. That's kind of how I think about it. So notice how in the problems we've seen so far, you could just figure out what terms multiply together and hey, something would pop out that works. But not every quadratic is possible to factor. And so if we want to be able to factor something anyways, to be able to solve it, completing the square allows us to do that. So completing the square has several different steps. That's why I summarized all of it on this slide for you. First off, we're going to put all x terms on one side and non-x terms on the other. So for example, we'll be looking at this. ax squared plus bx equals c. Your c will likely change in sign. Okay, just note when you move it to the other side, it'll move, become negative. If a is not 1, so if there's actually a coefficient in front like we've been seeing, we're actually going to divide each term by that a value to reduce it. Then this is going to be the weirdest thing, but we're going to add b divided by 2 squared to both sides of the equation. Now, since we're not doing it on both sides, we won't change anything about the equation, but you're going to see that now the left-hand side actually becomes something we can factor. And in fact, it's going to factor into something of this form. So then all we'll have to do is take the square root of both sides and we'll be able to solve for the variable. So let's see this in action. In this example, we have 2x squared minus 1 equals 3x. So first off, we want to move all of my x terms to one side, non-x terms to the other. To do that, we're going to have 2x squared minus 1 equals 3x, and I'm going to subtract 3x from both sides. Then I have 2x squared minus 3x minus 1 equals 0. But I want my non-x terms to be on the right-hand side, so we're going to go ahead and do that. And I have 2x squared minus 3x equals 1. Essentially add 1 to both sides to move the 1 to the right-hand side. But I need my a value to equal 1. Essentially, I need no coefficient in front of my x squared term, so I'm going to divide everything by 2. Basically, dividing both sides by 2 doesn't change the question at all, but I get x squared minus 3 over 2x equals 1/2. And yes, we can end up with plenty of fractions when completing the square. We just have to accept it. So now, with completing the square, we said, okay, if I have my a value is 1, so no coefficient for the x squared term, and I have 3/2 x, I'm going to add a little bit to both sides. And that little bit that I'm going to add is my b divided by 2 squared term. Well, b here, if we go back to looking at this version of the function, b is -3, right? That's the standard form part of the equation that we have. So b is -3, which means b divided. You know what, guys? I just misspoke. I don't want to look at that version of the equation. I want to look at this version where my a value is 1. So my b value is not -3. It's -3 over 2. Again, I want to make sure my x squared term doesn't have any coefficients in front of it. So I have to use this b value that ensures that that's true. Okay, so b is negative 3 divided by 2. So b divided by 2 is negative 3 divided by 2 divided by 2 again. Which, of course, if we do a quick fraction bit of work, I multiply by the reciprocal here. I'm looking at negative 3 divided by 4. So then I know my b divided by 2 squared term is negative 3 over 4 squared, which is 9 over 16. So now that is the term that's getting added on both sides. Now, it looks like that left-hand side would be absolutely awful to factor at this point, and we would not want to do it. But completing the square tells us that this leads to factoring of the form x minus b over 2 squared. And I know what b over 2 is. It's over here. So I automatically know my left-hand side is going to factor to x minus b over 2 squared. My right-hand side, well, 1/2 is really 8 over 16 plus 9 over 16. That gives us 17 over 16. And you can plug that in your calculator if you're not sure. Okay, well, this really on the left-hand side then is x plus 3 over 4 quantity squared equals 17 over 16. So now we square root both sides. Let me draw some lines. And we get x plus 3 over 4 equals square root 17 over 16. And all I got to do, you know what I just missed is my plus or minus. Always got to have that plus or minus when we take the square root of both sides. Again, we're undoing the square over here, and that puts the plus or minus on the square root. So now all I got to do is subtract 3/4 from both sides, and I get x equals plus or minus square root 17 over 16 minus 3/4. We can actually simplify this a bit, though. Of course, we want to break up our plus or minuses, but we also can look at the fact that we have root plus or minus root 17 divided by 4, because root 16 on the bottom there is a 4. If I take that square root and I just distribute it to this bottom term here, I get 4, this 4 over here. But now I have two fractions where 4 is my denominator. So essentially, my x is positive root 17, minus 3 over 4, or x equals negative root 17 minus 3 divided by 4. And these are my two x values. And again, it all came down to distributing that square root to the 16 on the bottom. So root 16 became 4. And then we can combine our numerators 17 minus 3 or negative root 17 minus 3. Now, that was all a lot, and it came down to some manipulation with different values. We had to divide by a. We had to take care of our negative b over 2 as the factor it squares to. All to say is if I did this with the general letters a, b, and c, the quadratic formula would pop out of that. So assuming that I do actually have an x squared term, that's what it means when I say a cannot be 0, then my solutions for x are given by this. You can memorize this formula any which way you want. I was taught a little song for it that I learned in high school, and it's just stuck with me literally ever since then. But there's all kinds of different ways to memorize it. I'm sure you can look it up online. I am not going to sing it for you now. But please do memorize this formula. Very important to get used to working with it. Really just comes down to plugging in a lot of a, b, and c values. But the harder part is dealing with the square root in there. So it takes a little bit of practice. So let's find the exact solutions and the approximate solutions rounded to the thousandths here with this function. So I want to write it in standard form first, as in I have 3x squared plus 2x equals 7, and I want to subtract 7 from both sides. And that gives me this. That means that a is 3. So remember, I'll write at the top, ax squared plus bx plus c equals 0 is the form. So I have a equals 3, b equals 2, and c equals -7. All right, so the quadratic formula is x equals -b plus or minus square root b squared minus 4ac all over 2a. That's our formula. Let's plug in all our values. So I get x equals -2 plus or minus square root b squared, great. 2 squared minus 4 times 3 times -7 all over 2 times 3. Now I like to double check. I got b squared, which is -2, plus or minus square root b squared, which is 2 squared, minus 4 times a times c all over 2a. Wonderful. Let's simplify a little bit. Starting with what's under the square root, I have 4, and then I have a -4 times 3, which is 12, then 12 times 7 is 84. So I have a -4 and a -7, that becomes a plus 84 divided by 6, 2 times 3. Okay, so this is -2 plus or minus square root 86 divided by 6. Let's think about this for a second. I have 88 would help. It is not 86, 88. And let's see, is 88 reducible? 88 is not divisible by 9. It's not divisible by 16, 25, 36, 49. What's next? 64? No. So 88 is not reducible. Just thinking through those kind of squares ideas that we covered in the worksheet. It as a square root. So actually this is just x equals -2 plus square root 88 divided by 6, or x equals -2 minus square root 88 divided by 6. And that is it. I'll let you put it in your calculator to see what it is rounded to these thousandths. But that's pretty much it for these quadratic formula equations. Now there's a particular term in the quadratic formula that's a little more interesting than the rest. So remember that the formula goes x equals -b plus or minus square root b squared minus 4ac all over 2a. And that b squared minus 4ac term that's under the square root is what we call the discriminant. See, this is actually what drives the number of solutions that we're going to have, if we're going to have any. So looking at if b squared minus 4ac equals 0, then there's only one real number solution. So you know you're not going to have a plus or minus, because plus or minus of 0 is 0 either way. You're going to be left with your minus b over 2a term. Now, if we look at b squared minus 4ac and it's positive, that's when we get two different real number solutions, essentially our plus or minus case. We'll truly have two different values there. Now, if b squared minus 4ac is negative, then we're trying to square root a negative value, which is not okay. So this is when you end up with imaginary numbers, not real numbers, as your roots and your zeros, but we're actually not covering that in this course. So you don't have to worry about this case in this course for now. So you might be asked, based off the discriminant, are we going to have one solution, two solutions, or only imaginary solutions? And this is what tells you about that. You just take b squared minus 4ac, look if it's positive, negative, or 0. Now, graphically, what this looks like is if I have x squared minus 3x minus 4, my discriminant is b squared minus 4ac, which is negative 3 squared for this first case, minus 4 times 1 times c, negative 4. Well, that's 9 minus, actually plus, because it's a minus 4 times a minus 4, 16, which is 25. That's positive, so that's why we have, and this all applies to this problem, that's why we have our two real number solutions here. We have a positive discriminant of 25 here, and so you see that we cross the axis at exactly 2 places. We actually have 2 solutions. Remember, zeros are where we're crossing the x-axis. Okay, so let's say now instead we're looking at something like G, where we actually have our b value, or b squared minus 4ac is 0. Well, that's when we have one real number solution, and when you look at the graph, it says, oh, my vertex is going to sit right on the x-axis. That's how we get exactly one spot on the x-axis, and it's the only way that that can happen. Now, we can also have quadratics like the third case that are completely above the x-axis, and that's when you have 2 different imaginary numbers as roots. You can't visualize imaginary numbers on a real number graph because they're imaginary, and you don't have to worry about them in this course. But visually, you should get used to saying, oh, this quadratic is never touching the x-axis, therefore no real number solutions, it only has imaginary solutions. Now we can also use equations that are of the same general concept of a quadratic and solve them similar to how we solve quadratics. So what I mean is, if you look at this, we have x to the 4th minus 5x squared plus 4 equals 0. And this is kind of the form if I took this x to the 4th and called it x squared squared minus 5x squared plus 4 equals 0. It's almost like I could say my a value here is 1, my b is negative 5, and my c is 4. Because I'm taking my first term and I'm squaring it, and then I have no exponents here. Again, if I call my variable x squared, then I have none in my third term. So it's like, okay, this is the general same format. Can we use similar techniques in order to solve this? And yes, actually, we can. And what we do is we say, well, I'm going to, instead of working with this x squared term, I'm just going to call x squared some u value. And then I'm going to take that u value and I'm going to look at u squared minus 5u plus 4 equals 0. And essentially do what we did above, but just take x's out of it entirely and look at solving u. And then we can actually do a last step replacement in the end and get the answer in terms of x. So let's see what that looks like. We're now going to solve u squared minus 5u plus 4 equals 0. Using our standard techniques, well, this guy actually factors. This factors as a u here and a u here, and I need things that multiply to 4 and add to negative 5. I'm thinking 1 and 4, since those two will add to 5. And then, of course, if I have a plus 4 on the end, that means I have matching signs. I have a minus in my middle term, so that's a minus and a minus. And this all equals 0. So now I get u minus 4 equals 0 and u minus 1 equals 0. Solving each of these, I get u equals 4 by adding 4 to both sides. And over here, I get u equals 1 by adding 1 to both sides. So now I was actually able to solve this function. But now they didn't ask me for a question in terms of u. They asked me for the solution in terms of x. Well, I know that u equals x squared. So I just pop the substitution back in, and I'm looking at x squared equals 4. And over here, again, I use u equals x squared. And I plop in x squared, and I get x squared equals 1. Okay, so now all I got to do is square root both sides, and I get x equals plus or minus root 4. And on the right-hand side, I get x equals, again, square rooting both sides, plus or minus root 1. And both of those are squares that reduce. I can get x equals plus or minus 2. And I get x equals plus or minus 1. So really, we have 4 solutions here. I could have x equals 2, x equals negative 2, x equals 1, and x equals negative 1. These are all of my solutions after doing that substitution. And notice the original problem had an x to the 4 term. So it should kind of get your brain going that you might have 4 solutions in total. And this is how we solve it. You do have a homework question on this, by the way. Now we're going to talk about applications of quadratics. So for our first example, magazine closures. The number of both magazine launches and magazine closures have increased in recent years. The function, m of x, given there, can be used to estimate the number of magazine closures after 2012. In what year was the number of magazine closures 99? First, we want to think about what is our input, what is our output here. This function written down says it estimates the number of magazine closures after 2012. So our output is certainly the number of magazine closures. The input is the number of years after 2012. That's going to help us be able to understand how to answer the question, in what year was the number of magazine closures 99? Because now we know the output is 99 and we're solving for the input. So let's go ahead and do that. And we want to write down our function m of x equals 34x squared minus 59x plus 81. I'm just going to double check that I have that right. 34x squared minus 59x plus 81. Yes. And so now we're going to substitute 99 for m of x. 34x squared minus 59x plus 81. And we want this equal to 0, so we're going to subtract 99 on both sides. Get 0 equals 34x squared minus 59x minus 18. Now to solve this, we're going to use our quadratic equation, which is, of course, x equals negative b plus or minus square root b squared minus 4ac all over 2a. So, of course, in our question, we have a is 34, b is negative 59, and c is negative 18. And so we get x equals negative 59 plus or minus square root negative 59 squared minus 4 times 34 times negative 18. My goodness, over 2 times 34. Well, luckily, this simplifies to x equals 59 plus or minus square root and 5929 all over 68. Now, shockingly, 5929 is actually a square. If you put it in your calculator, you get 59 plus or minus 77 over 68. But that is just 59 plus 77 over 68, or 59 minus 77 over 68. This is where we break up the plus and the minus. We handle them separately. So do 59 plus 77 is 136. And 136 divided by 68 is 2. What a nice whole number to end up with. Or 59 minus 77 is negative 18. And let's just write that down. Negative 18 divided by 68, which is, of course, negative 9 over 34. And that's as much as we can reduce that one. But those are our two values. Now, of course, we don't take the negative value because we're not going to go back in time for this problem. We're just looking forwards in time, 2 years forwards in time. And if we plug that in, if we think of what is m of 2, just to check our work, that was 34 times 2 squared minus 59 times 2 plus 81. And we check that, 34 times 4 minus 59 times 2 plus 81, we do in fact get 99. So we can sum it up with the question, with the sentence down here. Thus, there were 99 magazine closures in 2 years after 2012 or in 2014. For our next example, we're thinking about a falling object. So we're going to assume a ball falls from a building of a height of 144 feet. And anytime an object is falling, it's given by the formula S of t equals 16t squared. It's used to approximate the distance s in feet that an object falls freely from rest in t seconds. How long will it take for the ball to hit the ground? So what we want to do is think about, well, if I have a ball falling at 16t squared, then I want to know when it hits the ground. I want to know when it's gone 144 feet. So we're going to take our S of t and 16t squared and set it equal to 144. Right? Our input is time. Our output is the distance that it's actually fallen. And so we want to know when it's fallen 144 feet and solve for time to know when the ball hit the ground. So if I divide 144 by 16, so we're dividing both sides by 16, we get t squared equals 9. I take the square root of both sides, and of course I get t equals plus or minus 3. But of course, the negative doesn't make sense in this context, so we get t equals 3 seconds. And that's it for this problem. If you have any questions, as always, please feel free to reach out. Thanks so much for listening.